Hello everyone, welcome back to my session on DA lab programs. In today's session I am going to discuss about divide and conquer. Under that divide and conquer I am going to discuss about merge sort program. Basically what actually happens in merge sort is we apply a divide and conquer method. Under divide and conquer method what we exactly do is we take a big problem and this big problem is divided into sub problem. Again the sub problem is divided into sub problem. And again this subproblem is divided into subproblem. Once the solution is identified at each subproblem, this subproblem becomes a original resultant problem solution. This is the idea of merge sort. Okay. The given problem will be divided into subproblems and each subproblem will be divided into multiple subproblems. Finally, we add all the subproblems to obtain the original problem. Okay. In this context, we have an example here, any problem for that matter. We apply a divide and conquer method. The problem is divided into two sub-hops. The moment n value is more than 1, when n value is greater than 1, we have to divide the elements. In that context, the values are divided into two subproblems, subproblem 1, subproblem 2, etc. until the subproblems are divided into number of elements taken as an input. Okay. At each juncture, we are going to solve the subproblem. The subproblem solution will be taken as the original solution. That is the main idea of divide and conquer method. Okay. Here is an example. We have the algorithm, a pseudocode kind of an algorithm. Okay. The algorithm name is D and C. D is nothing but divide and C is nothing but conquer. P is nothing but problem. In this context, if small of P, then written as means when the problem is small, when element is only 1, we have to return that particular element alone because that is the only element exists in the array or given element is 1. In that case, this is the only element is there. So we have to return the small subproblem as that element alone. In that context, we are going to have this S of P. Suppose if the element is more than n, more than 1, I beg your pardon, more than 1, in that context, we are going to divide the element into multiple subproblems. Then each subproblem is divided into divide and conquer method and later the subproblems are combined as a original solution. That's what we can see here. If you take an example here, a work is there, a huge work task is there. Generally what happens, a big task, we alone cannot manage big task. So what happens is we escalate to n number of co-workers or subordinates. So that what happens, those subordinates, those co-workers will work that sub-task or individual responsibility will be assigned to them. Once they find the work completed, we will integrate it. We will collect all those work and we represent to the higher up that the work is completed. It's like any other conference or an event, FDP program, IEEE conferences or any program, inauguration program. We divide the work to n number of people of the institute. And later all these people participate and that participation is nothing but the solution for a given program. So similarly, a work has been divided into n number of sub-workers. Later, the n number of workers are going to work on individual solution R1, R2, R3 and finally the solution is obtained. That solution is nothing but the solution for the given original problem. This is one of the definition of divide and conquer algorithm. Then merge sort. Because the merge sort comes under divide and conquer method because here also we apply the divide and conquer technique. What exactly happens here is when n is equal to 1, we say that is the only element which is sorted. Okay, we are not going to apply the merge sort. But when n is greater than 1, in that case, definitely we would like to apply the when n is greater than 1, in that context, we divide the element into two sub-parts. Okay, this subparts again will be divided into micro level of subprograms. At each level, we are going to obtain the solution. This solution will be a solution to the original problem. original problem. That is the idea of the merge sort as well as. Okay. In this algorithm, we generally say the merge sort in terms of worst case. Worst case is big O of n log n. I will compute this value at last of this session, how this n log n comes into the picture. Okay. Okay. The divide and conquer strategy is applied with respect to merge sort. Here we divide the element into two sub halves and we are going to find the solution and we are going to get the problem solution. Then in this context we have an algorithm, okay, the merge sort algorithm. How the algorithm looks like, for example, if you take the elements here, I take array of 10 elements, n is equal to 10, okay, means 1 to 10. Okay, my array index starts from 1, so it is 1 to 10. If it is starting from 0, it is 0 to 9. Here I am starting from my array index from 1, it is going till 10 elements. Okay, 310, 285, etc. until 520. Elements are not in the order, it is unordered. It is unsorted or unordered. Unsorted or unordered. In that context, we would like to sort this element using the merge sort application. I said right how the merge sort works. The merge sort works on the principle of divide and conquer. Means I would like to take these elements. Divide into two sub hearts. Okay, if I take these two sub hearts, okay, a of 1 to 10 is nothing but my given problem. If I divide this given problem, okay, it comes to 10 by 2. If I divide by 2 sub hearts, 10 by 2 is nothing but 0 to 1 to 5 will be one particular set elements and second element will be 1 to 6. Okay, this is my sub part 1 and 2 initially. Next again there are 5 elements are there. 5 by 2 if you do it, you get 1, 2, 3, 4, 5. This will be your sub part. Again 5 elements are there, you get 6, 7, 8, 9, 10. Okay, you get 2 sub parts. Again when you divide it, 1, 2 comes here, 3 comes as a sub part and 4, 5 comes here, etc. It goes on. And finally at every moment, at each sub problem, we would like to swap the elements. Okay, how the swapping of the elements happens means is given in this algorithm. You can see here merge sort low comma high means I have a given element. Okay, this is my low and this is my I. Okay, this is my I starting from 1 to 10. Starting from 1 to 10 or 0 to 9 as per our index of the array what we are going to consider, we can use it. Okay, what happens here is if the elements are more than 1, in that case I would like to divide the array. Okay, suppose elements are 10, n is equal to 10, then I would like to divide my n is equal to 10. So in that case what happens, to find the mid value I would like to take low plus I. My low is 1, okay, plus my high is 10. This is nothing but 11 by 2. 11 by 2. How much it comes? 5 point something will come. In that case 5 will be my mid value. 5 will be my mid value. So mid is equal to low plus high by 2. So 5 will be my mid value. 1 to 5 will be first sub problem, and 6 to 10 will be the second sub problem. Okay, this is the first thing we are going to divide it. Okay, once it is done, I'll get 2 sub part. One is the left side part of the element, low comma mid, and I'll get right part of the element, mid plus comma high. This is mid plus 1. Right part of the element, it goes till the high value. Okay, my left part of the element starts from low, it goes till mid value. That's what it's given here. Finally, we have to solve the left part of the sub problem and we have to solve the right part of the sub problem. Once we solve the right and left part of the solution, then we obtain a original values of the given element. That particular task will be accomplished by merge function. So that we have that low value, mid value and high value. So which is going to cover the complete elements of the merge sort which was already unsorted. With the merge sort application, we are going to sort the element. Okay, let us take an example here. We have array of 6 elements starting from 0 to 5. Okay, so we have elements like 6, 1, 4, 3, 9, 8. Okay, in this case 6 by 2 I am going to divide it. It's nothing but 3. So initially my first half of the element will be 0, 1, 2. Second half will be 3, 4, 5. Okay, then my first half of the element will be 0, 1, 2, and second half will be 2, 4, and 5. Okay, again we have the scope of dividing the elements because it's more than one value, n is more than 1 here. In that case, again we have to divide the value. So 2 by 2 is nothing but 1. So 0, 1 is one particular subproblem. The remaining value of 2 will be retained with the fourth value. Again 1 is there. 1 by 2 is what? We get 1 for each individual index, 6 and 1. That's what we got, 6 and 1. And 4 is written in the second position itself. Now what happens? The same procedure is applied in the right part of the array elements. 3 and 4 will have 9 and 8. And 8 will be at the fifth position, and 3 and 9 will be divided again with respect to the by 2 value. Again, between 3 and 9, 3 is lesser, so 3 comes left side, 9 is bigger, so it is there. Again, we have 8 value here. Between 3 and 8, 3 is smaller than 8, so 8 is retained here. And between 8 and 9, 9 is bigger, so it goes right. So this part of the solution is second solution we got in the right side. Coming back to the left side, between 6 and 1 is smaller, so it comes left side, and 6 is bigger, it goes right side. So this part of the index of the array elements are sorted, but one more element is left out. So compared to 1 and 6, 4 is bigger than 1 and lesser than 6. So in that case, it has to be placed in between 1 and 6. So it's 1, 4 and 6. Right side part, it is 3, 4, 8. Again, if you see from this particular elements, although the elements are sorted in this sub-solution 1 and sub-solution 2, but they are not completely sorted. So this will be the final array, the auxiliary array. This auxiliary array, which will have the final sorted elements. In that context, 1 and 3 is compared. 1 is smaller, so it will be retained. Between 1 and 8, 1 and 9 is seen. No, 1 is smaller. Next you take 4. 4 and 3 is bigger. Okay, so in that case 3 is smaller, 3 has to come here. 4 is smaller than 8 and 9, so 4 will be there. Next if you take 6, 6 is bigger than 3, already we are there in the index, and 6 is lesser than 8 and lesser than 9, so 6 is there. Already 8 and 9 is sorted, so we retain the 8 and 9 value in the respective indexes. So this is the final solution. For the given elements of the original array elements. So now when we see a recursive kind of array, the algorithm here, okay, see what happens is, here we have the consideration initially low, high, global variable, and mid plus 1 to high, okay. Then low and high are the thing but the index of the elements, starting from, this is my low, this is my high, somewhere in between the mid value will be there. Initially my h is equal to low, my h will point to the low element. And my j will point to I will point to my low element again. My j will point to mid plus 1. Mid plus 1 means the right part of the element. What happens here means, if h less than or equal to mid and j less than is equal to high, means what I have to do is I have to take care of the left part of the element. Left part of the element means a of h less than a of j. A of s less than a of j means this part. Okay. My low, this is my high, this is my mid value. This is mid plus 1. Okay. So I have to consider the left part of the elements now. with respect to this condition. If A of H less than A of J, then B of I is equal to A of H, then H plus 1 means I have to take the left part of the element, and dump into the array. Left part of the element dump into the array. Okay. So next, if you come, the other condition is if a B of I is equal to A of J, J is equal to J plus 1 means what? We are going right part of the J is nothing but mid plus 1. Mid plus 1 means right part of the element. In that case, I have to check the right element. Then I have to copy that element to the auxiliary global array. This is the auxiliary global array. B of something is there, right? This is nothing but your auxiliary global array, or it's nothing but a temporary kind of array, where we are going to dump the elements from both the left subproblem and right subproblem, and we are going to copy the sorted element in the global auxiliary array before copying to the main array. So this is the thing we are going to do it recursively as I is incremented by 1. This can also be written as I plus plus. We can also write as I is equal to I plus 1. So what happens is, if H greater than mid means once the condition is going H greater than mid means my H is pointing here initially, greater than mid means right side I have to check. Right side means, suppose you can see here 14538 is there. In that case, still 9 is there. 9 is bigger. So I have to copy that 9. to the auxiliary memory. In that context, so I have to look forward for that extra element, whichever is there, I have to copy to that auxiliary memory. Whatever the extra elements are there, I have to copy to my auxiliary memory. What is that auxiliary memory part? So this 9 has to be copied to the auxiliary memory. So this part we are going to do with respect to this condition. Again, else for k is equal to catch is equal to mid do means what? Within the left part of the element, if anything is left. Suppose here, suppose 9 is stopped. Suppose some more elements are there. Assume that 5, 2 something is there, etc. Some more elements are there. In that case, these elements also I have to copy to the auxiliary memory after sorting. In that context, again I have to look forward for that element and copy it. Finally, all the values of the elements, whatever is left out from the left sub part solution and right parts of the solution, will copy to the global auxiliary memory. Global auxiliary array. That array will have the sorted version of the element. Element will have the shortest version of the element. That is nothing but B of k. B of k is nothing but sorted. Sorted order of the element. Elements. So this is copied to the main array. The main array. What is that main array? A of k. A of k was the initial array. Now with this B of k which is having the sorted element, initially A of k was the element which is unordered, which is not sorted. Now B of k with all these combinations of left element checking and right element checking by divide and conquer method, we have found the solution. That solution is stored into the B of k auxiliary global array. That temporary array elements again we are going to copy to the original array. This is the concept of your merge process with respect to the merge sort algorithm. Now what is the position we have considered? H, I, J and A low and mid plus j, etc. It all belongs to this particular example. You can see here. Okay, H is nothing but pointing to the first index of the solution 1, J is pointing to the first index of the solution 2, and I is pointing to the first index of the final solution 1. I is pointing to the first index of the final solution 1. That's what it's written here. Okay, the animated version of how the merge sort is going to work. Have a please look at it. Initially, we are going to take the elements. We are going to divide the elements using divide and conquer method. The elements are going to get scattered. Again, based on the comparison between the elements, lower or higher, we compare the intermediate elements. Then we are going to sort it. The sorting order will give the solution to the final problems question what was given earlier. 5 and 6 will come here. Again 7 and 8 will be compared with 2 and 4. 7 will go here, 8 will come here. Again this particular subsolution 1 and subsolution 2 again will have a comparison. Then while comparison, based on the comparison of the value, we are going to sort the element. 6 will come here, 7 will come here, and 8 will come here. This will be the final solution of the merge sort. Whatever was explained, it has been briefly given here. We have a set of elements. Using the merge sort, we have divided into two sub problems, and the left side will be the element which is less than the mid value. Okay, mid value. The mid plus 1 is nothing but right part of the element. It goes till high. It starts from low in terms of elements. Okay, low to mid is nothing but your left sub part of the element, and mid plus from high is nothing but your right part of your element. Okay, the algorithm what was explained, it has been detailedly explained here. Initially we take the elements low, high, mid, etc. Then we check the elements. Then we copy the elements to the left side of the array. Then we copy the elements to the right side of the array. Then anything left out elements are there to copy to the main auxiliary array. We are going to copy left out elements, the higher part of the value, the right side part of the array elements. Then anything left out in the left part of the array elements will be copied to the auxiliary memory. Finally, the auxiliary memory is copied to the main array. Then we are going to compute the time complexity of this merge sort using recurrence relationship. Okay. Now you can have a notice here. To find the recurrence relationship, we have to have initial consideration. Okay. We go off in to do merge sort complexity process. Cn is nothing but number of times to complete this merge sort. Okay. Some constant n number of times is required for a given set of element to merge it. Okay. Suppose if n is equal to 1, I can say it's a constant time, some a or k or p or something else, etc. No problem. But the moment n is greater than 1, okay, then in that context we have to divide the elements into the left problem and right problem. Like what we have divided here. This is the left part of the problem and the right part of the problem. In that context, this is left side, this is right side, because when I am using merge sort, it's divide and conquer method. So n is divided into two halves, n by 2, n by 2, n by 2, n by 2. And for those elements, after dividing, we have to merge it. So we have some constant number of times to merge it. Okay, that's what this some constant n times is given here. So given t of n is equal to a, some constant a, when n is equal to 1. When n is more than 1, okay, we have to divide n into 2 times. Okay, n by 2 plus t of n by 2, t of n by 2 1, t of n by 2 another 1. Okay, 1 plus 1 is 2. So the 2 times of t n by 2 plus n, some constant n, is the given recurrence relationship. Now we have to apply the backward substitution method. Okay, so when you apply the backward substitution method, my 2n of n by 2 plus cn is the given equation. When you apply this value for this equation, given value of t of n by 2 plus cn, we get 2 into t of n by 2, because n by 2 into 2 becomes what? N by 2 into 2 becomes 4 plus constant into n by 2 plus cn. Okay, so next cycle 2 into 2 becomes 4. Again the 4 is retained. This is generalized here. 4 of t by 4 by cn plus cn. And as we proceed with the backward substitution method, we keep on incrementing the n value. Okay, it goes on. At some point of time, we have to generalize the equation. Okay, we have to generalize the equation with some particular assumptions, like x is equal to log to the base 2 power x, etc. In that context, we can change the log n to the base 2 to log n to the base to 2 power I. Okay, so this can be written as like this, as equivalent to log n to the 2 power x to the x. The same thing is replaced here. So this replacement we can replace with the given equation T of n is equal to n plus n, T of n plus Cn, some log to the base 2n. Okay, so T of n is equal to A of n plus Cn log n to the base 2. In case to replace any asymptotic notation, we can say it is as big O of n log n, because when you consider some constant n log n compared to the 1 n here, the bigger value is n log n to the base 2. So this is bigger compared to the n value. So we are going to consider the big O of n log n as the complexity for the worst case of the merge sort. The same method, the same recurrence relationship, okay, using backward substitution method, we have used this other method, the same steps only, but we have used some other different method. We have taken the merge sort value left half of the problem and right half of the problem, some constant value, okay. Then we are applying the substitution method. While applying the substitution method, we take all these power values or some k, okay. All the power values of n is nothing but we take some 2 power k, because 2 power k means what? 2 power 2 is what? 4 and 8, 16, 64, okay. When we take 2 power some value, we can divide the elements into even numbers. See, if I say 2 power 2, it is 4, right? So when you divide 4, it is 2 and 2. Again, when you divide this 2 and 2, it is 1 and 1 and 3 and 4. Okay? Like that, we can have the equal proportionate of the dividing of the elements. That's the reason we can take n is equal to 2 power k. Accordingly, replace in the given generalized equation. As we replace the generalized equation, my n by n goes here because 2 power n is nothing but n. So I replace that 2 power n by 1. So 1 by 1 is nothing but 1. So T of 1 is nothing but given as a, and this n is retained. This completely is nothing but n power 2 log n as per this given assumption. In that context, between 1 n and log n to the base to the n value, this log n to the base 2 is nothing but bigger. So we retain big O of n log n as the complexity of merge sort in terms of the worst case. So I am going to give a demo on the problem 3 of DA lab. Okay. In this context, initially the execution starts from the main program. Let us go to the main program. This is the main program. Initially we have the local variables. We have two variables here. One is for seconds. This is for microseconds. S is for seconds. And this US is nothing but for microseconds. It's for microseconds. So I have a milliseconds, one double variable. Then struct time val struct end start is nothing but the structure variable of time val type. Okay. We are going to use it for checking the time complexity of the system. Okay. Initially we are supposed to enter some n elements. We are going to read it. Okay. We are going to take the allocation of variables from the heap memory. Okay. Somewhere in the concept we have a heap memory. Okay. This heap memory, suppose if you take n is equal to 5. Okay. So I have taken int of star is a pointer variable because we are referring to the memory. It's nothing but a pointer variable. Okay. Pointer request. So calloc is dynamic allocation of the memory. N comma size of int. N comma size of means my n is 5. Size of int is 2. Okay. So 2 into 10 is nothing but 20. So 20 bytes of memory, 20 starting from 0 to some particular value, 19, because if it starts from 0, it is 19. This many, each block is nothing but of 2 bytes. Okay, 2 bytes. In that context, so what happens? 2 into my n value is 5. In that case, it is 10. Okay, I am going to take only 5 blocks because my n value is 5. I just by mistake I written 10 there. 2 into 5 is nothing but 10. Okay, in that context, 5 blocks of integer type of location memory I can allocate for this particular request. So random of modulus of n is nothing but randomly I would like to generate the number. That generated number of n will be stored into the A of I array. Okay, that I am going to print it. Okay, now what is happening is there is a method called get time of day ampersand start comma 0. Okay, it is a function which is part of your timestamp.header file. Okay, this particular function, why we use it is, we would like to take the current system time starting time before starting the algorithm. Okay, and comma 0, this 0 we make it as 0 because it is pertaining to GMT time, Greenwich Mean Time. Okay, we are not going to consider too much about that GMT time, so that's what we have mentioned it as 0. That's what we have maintained it as 0. Then we are invoking the merge sort. Okay, merge sort starting point array, starting point n minus 1. N minus 1 means what? N is equal to 10 means 10 minus nothing but 0. 10 minus 1 is nothing but 9. Okay, in that context, we are going to invoke the merge sort function. So that this call goes to this particular function merge sort. It has a array low and high. It has an array and low and high, and we have a mid value. Why we have a mid value means because if elements are more than 1, we would like to divide the array into 2 subparts, left subpart and right subpart, or left subproblem or right subproblem. Then in that case, low less than high means we are going to divide the elements are more than 1. In that case, mid is equal to low plus high by 2. So this will becomes the left part of the element of your array, and this part a comma mid plus 1 becomes the high part of the array. A comma low comma mid is nothing but left part of the array. Left part of the array, left part, and this is nothing but your right part. Right part are subproblem 1, subproblem 2, whatever the context we can represent it. Later, once we sort this left subpart and right subpart, both we have to merge it. That's what we are going to use, merge a comma low comma high comma mid, because while merging we have to start from low to mid. That's what mid is also included, and from mid to high also whatever the values are there we are going to include in the merge algorithm. In that context, the moment the call comes to merge, okay, it goes to the merge function. Here also we have a array low, high and mid value. Okay, and we know why this dynamic allocation is done, because to take the memory allocation for auxiliary memory. That auxiliary memory is nothing but your C of k. This is nothing but your temporary or auxiliary memory. Okay, auxiliary memory. Initially low is I is equal to low, mid is equal to mid plus 1, k is equal to low. That's what this condition is nothing but, if I less than mid, I less than j means left part of the array, left part of the elements we are going to sort it. That's what this example is as equivalent to this part. Okay, this part. Okay, left part of the element, this is an algorithm. In programming paradigm we have used a different variable. Left part of the elements we are going to sort it. Next, that's what we have done here. Okay, left part of element is done. Again we have to check the right part of the element. The right part of element is given here. Key of k is equal to a of j. A of j means it goes to mid plus 1. It goes to mid plus plus. In that context, because you can see here j is nothing but mid plus 1. It goes to right part of the element. The right part element, whatever is there, you are going to copy into the C of k. The C of k. How it is going to happen is, you can see here, this part. Now again, once we have completed both the left hand elements copying to the auxiliary memory, this condition is there, h greater than mid, then copy the left out right side element, and left out left side elements. The same thing is applied in the program as well, as whatever the elements which is left out in the left side element, and right side element, that should be copied to the auxiliary memory. That is nothing but C of k. Okay, there in the explanation of the algorithm, which is B of k, in this program we have used as C of k. So what happens is, completely the auxiliary array, which is nothing but C of k, will have the sorted element. That sorted element copy which copied to the main array is nothing but A of I. Initially my A of I will be having the unsorted element. Once we copy the element from C of I which is having the sorted element, that sorted element copied to the original array. Then whatever the memory we have taken from the heap memory, that we have to free it off, because that can be used for next any memory allocation for various other requests of the system resources. In that context, we have to free this memory taken for the temporary allocation of the global array here. In that case, that will be left out, that will be released. So finally what happens? So those things are going to happen is merge sort. Then after that complete merge sort operation and merging operation, we are going to end the algorithm. The complexity, that system time complexity, we are going to end here, ampersand end. This will be having the ending time. Then we are supposed to print the array. We are supposed to print the array, which is going to have the time complexity of sorted elements. Time complexity of sorted element. In that context, I am going to print the seconds. To print the seconds, I have to take the end value. End minus start will give my seconds value. Then in terms of microseconds value, end minus start, if you take it, that gives my microseconds value. Finally, I would like to also compute the milliseconds value. In that context, after printing the seconds and milliseconds value, I am going to compute the milliseconds time as well as. So second into 1000 plus microsecond by 1000 plus 0.5, this particular equation or the calculation will compute my milliseconds. So that is also I am going to compute it. And finally, I am going to free the array which was taken in the initial point, the array element A, which was taken in the initial point. That array, whatever the element was taken from the heap memory, that also will be read. In the merge sort, we had merge algorithm, we also release the temporary global allocation of the array elements, and here also the main array which was taken from the heap memory with the help of this calloc n size comma size of operator of int data type size, that is also freed. So that it will be useful for some other purpose. Let us see now. Let us see how it can be executed. Okay, you can run the program cc merge.c. Then this will compile the program, checking for the syntax and semantics of the program. If you don't have any syntax and semantics or any logical issues, then the exe format can be seen in ./a.out. Then you can enter the number of elements. Once you enter the number of elements, the elements will be sorted. Some time will be generated. Some time will be calculated. What generally happens is, as the today's systems are quite higher end, the processor speed is quite faster. In that context, if you take elements like 20 or 50 or 100 or even 500, the computing time cannot be calculated, the time complexity cannot be drawn, okay, or graph cannot be drawn properly, because it will take nanoseconds time to print the complexity of the time taken to run that particular sorting of the elements. So in that context, we have to take larger values. Like 25,000 and 50,000 and 1 lakh and 2 lakh, something. If you take that larger element of the value as an input, definitely the complexity value gets changed up. Then we can see the graph, the x and y axis. We can see this is nothing but number of elements. This is nothing but your time complexity taken. Then we can have a proper linear graph obtained for a merge sort. For that purpose, we have another method called, we can create a text file, merge sort.txt, in the gedit notepad, and we can run this xgraph -t merge sort -x. -x is value, -t is nothing but my y-axis is nothing but your time complexity part, my x-axis is nothing but number of elements, where we can use it for checking the time complexity, how much of time taken by the system to run it. In that case, once you give this one and run it, a graph will be obtained. The graph looks like that. Okay, this is nothing but number of elements. And the x-axis, this is nothing but your number of time taken for the elements to be sorted as a time complexity part. Okay, whatever the values are there, if you multiply with 10 power 3, that many elements is nothing but elements sorted by the system time taken with 10 power 3. So this is an example of how a merge sort is going to be implemented with the help of divide and conquer method. I am also going to show the execution part of this particular program. I just open an online compiler. This is the program I copied to the online editor, online compiling editor. I am going to run it. See, now the number of elements is requesting. Okay, I just say it's around 25 elements. Then I say enter. You can see there randomly it takes some 25 elements, and those 25 elements are sorted with the help of merge sort. And we can see this 0.5, irrespective of how many or number of elements if you take it, okay, you can see if I take 100, if I take 100 and enter, there is not much change in the time taken for the running this algorithm, because it's showing 0.5 only, 0.55000 only, because the elements are less. The elements are less. So you have to take more values. So you have to take more values, like 1000. See, still for 1000 values it is less. So you have to take around 25,000 or 50,000, 74,000, etc. The moment you take the longer value or the larger value of any value, in that case definitely we can see the change in the time taken for sorting those elements by the system. So with this note of demo of merge sort with the divide and conquer method, I am going to wind up my session. Thank you so much.